Hi students, we are back to solve some more problems here. So the first question says, if you have 10 grams of butane, how many grams of water can you make upon combustion? So usually in these types of questions, we start by writing the given, which is 10 grams of butane. But the thing here is we're going from butane to water. So we're switching from one substance to another substance. So when we switch from one substance to another substance, we have to do a conversion factor called the mole to mole ratio. And you can't do the mole to mole ratio unless you have the balanced equation. So this question doesn't give us the balanced equation, but we definitely know how to do a combustion equation, and we're given the hydrocarbon that we start with. So I'm going to go ahead and write that equation up here. So we have C4H10 in the gas form. And then we're going to react that with oxygen because that's what we do in combustion reactions. And in a combustion reaction, you're going to create which two products? CO2 and water. So we learned this in another chapter, and we also did balancing equations. So we know how to do that also. So we balanced this exact same equation, and this was one of those ones where we had to double all the coefficients. And we found that we had to have coefficients of 2, 13, 8, and 10 for this equation. So now we can see all the coefficients and we can solve this problem. So we can go ahead and go to the part of the question that we're used to doing first, which is writing out the given. So we have 10 grams of butane. Now whenever we have grams, we want to go where? To moles, that's right. So we have to use a conversion factor called the molar mass. So here we have the molar mass of butane. And we're going to let our units guide us. So that will tell us that we're going to go ahead and put grams of butane in the denominator here because we want it to cancel out. And if you guys need to draw a 1 under the butane there to remind yourselves that there's a numerator and a denominator there, go right ahead. If you don't need it, that's okay. All right, so in the molar mass, we have moles and we have grams. And whenever we have a mole, we put a 1 next to it for the molar mass, which is completely different from the mole to mole ratio. So here we have 1 mole of butane, and we need to figure out how much 1 mole of butane weighs. So what you would do is pull out your periodic table and see that a carbon weighs 12.01 and add up 4 of those and then add to it the weight of 10 hydrogens. And what you guys will find is that it is about 58.12 grams. Now we've canceled out the grams of butane here, and we're in moles of butane. And we know that we're not to water yet because we're in moles of butane. So we need to get from butane to water somehow, and we're probably at the point in the equation where we're a little bit stuck and not knowing where to go. So again, ding, 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 that should set off alarm bells in our brain to tell us that we're at the mole to mole ratio. So we let our units guide us, and we know that we want to get rid of moles of butane, so we go ahead and put it on the bottom here so it will cancel out with the numerator in the previous conversion factor. And I'll just label this down here, mole to mole ratio. And And what we want to do is we want to go to moles of something else because this is a mole-to-mole ratio. And what are we looking to go to? Well, that's water. So we go ahead and we put H2O here. Now in the mole-to-mole ratio, we don't necessarily put a 1 next to the mole like we did over in the molar mass. So we have to be careful here. And where we find the numbers that go right here and right here is right off of the balanced equation. So if you look up at the balanced equation, you can see that for every 2 moles of butane that we burn, we are going to create 10 moles of water. Now, of course, you can reduce that to 5/1, but most of us will just leave it there at this point, just so we don't have to simplify things and do some extra math. Now, you can see how if you didn't balance the equation properly and you had the wrong coefficients up here, it would mess up your entire calculation. So you want to make sure that you know how to balance equations. Now we've canceled out the moles of butane and now we're in moles of water. But the question doesn't ask for moles of water, it asks for grams of water. And we know how to get there. We can use the molar mass of water because the molar mass relates moles to grams or grams to moles. So we let our units guide us and we know that we need to have moles of water on the bottom over here. And again, in the molar mass, we're going to put the number 1 next to moles. So this is the molar mass of water. And that means we're going to have grams of water on the top. Now we've calculated the molar mass for water in another problem, and we found that it was 18.02. If you have 18.01, that's fine because that last value right there, that's where you have your estimation or your unsure point. Remember all the way back when we did significant digits. Okay, so the moles of water cancel out, and what we will get is 15.5 grams of water. And we did 3 sig figs because that original number has 3 sig figs. And this one has 4, and that one has 4. And all of the rest of our numbers on here are exact numbers, so they have infinite numbers of significant digits. So we ignore those when we're looking for how many sig figs we put in our answer. So there we have 15.5. Now number 2 says, how much oxygen do you need in problem 1 if you'd like to produce 7.39 grams of CO2? So this is kind of working backwards. We see that we want to produce a certain amount of product here. So we want to know how much reactant we need. And this is particularly useful in industry when you want to make a specific amount of whatever it is you're making, say like plastic. You need to know how much of your starting material you need to order. So you need to do these calculations. Thankfully, we have already done the balanced equation for this problem, so we can go ahead and go with our given, which is 7.39 grams of CO2. So we need to know if we're going to make 7.39 grams of CO2, how much oxygen we need. And we're in grams, and whenever we're in grams, we need to go where? To moles, that's right. So we're going to have grams of CO2 in the bottom here, and we're going to have moles of CO2 in the top there. Now that conversion factor is the molar mass of carbon dioxide. And in another problem, we calculated this to be 44.01. So we've canceled out the grams of carbon dioxide. Now we're in moles of carbon dioxide. So we know if the units are guiding us, we're going to put moles of carbon dioxide down here. Because we know we want to get rid of that, and we want to get where? To O2. Okay, so this means that we're switching from one substance to another substance, so that should alert you to the fact that you need a mole to mole ratio, and that's good because we already have moles in the denominator of this conversion factor. So here we're going to do moles of O2. Now, where do you look to find the numbers that go next to the mole for each of those values, the numerator and the denominator? Well, you look up at the balanced equation. And in the balanced equation, we can see that for every 13 moles of oxygen that we burn, we're going to make 8 moles of carbon dioxide. So you have 13 here and you have 8 here. Now, if the mole thing weirds you out, cover it up with your finger and read it this way. For every 13 O2s that I burn, I'm going to produce 8 CO2s. And that should make it a little simpler for you. Okay, so we cancel out our moles of CO2, and we're in moles of O2. And the problem says how much O2. Now, it seems like we could stop at moles there, but when you order chemicals, you're not going to order them in moles. You're going to order them in grams or milligrams or some kind of volume if you have a liquid or a gas. So we're going to need to go to grams here. So the conversion factor that we need to use needs to get rid of moles of O2. It needs to go to grams of O2. And when we relate grams to moles or moles to grams, what is that conversion factor called? A molar mass. And in a molar mass, we're going to have a 1 next to the mole, and then we have to figure out what the mass is for whatever substance we're looking for. Here it's O2. Now, a really common student mistake is to look at the periodic table and put that oxygen weighs 15.999 or 16.00. But what we see here is we don't have a single oxygen atom. We have the oxygen molecule, O2. So there's 2 oxygens there. So we need to account for that in the mass. So we have canceled out moles of O2. And what we find when we calculate this with our calculator is we have 8.73 grams of O2, and we did 3 sig figs because we have 3 sig figs there. We made this conversion factor to have 4 sig figs there and 4 sig figs there because convention states that we usually want to go to 1 more sig fig than the original measurement, if at all possible. If you can only have the same number, that's okay too, but you don't want to go less than. So we wouldn't want to have a conversion factor that had 2 sig figs in it because we don't want to restrict the number of significant digits if that's possible. Okay, so there's our answer there. And then number 3 says how much carbon dioxide is produced upon combustion of 4.3 grams of propane. So no longer do we have butane like we did in questions 1 and 2. We have a different gas, propane. And this is one of the gases that's popular for uses in barbecues. So I'm going to erase number 2 just to give myself a little more room here on this slide. And for number 3, what we're going to do is instead of starting with 4.3 grams of propane like we usually do, we're going to have to go ahead and write out the balanced equation first. So we have C3H8, and it says combustion. And we know what a combustion equation looks like at this point. You have a hydrocarbon, and you burn it with oxygen, and you produce 2 products, carbon dioxide and water. And don't freak out if water is written first as a product. They both come out of the reaction, so they can be written in either order. And then we need to balance this equation here. And we've done this before, and we found that for every 1 propane, you're going to need 5 O2 molecules. You're going to produce 3 CO2s and 4 waters. And if you need to balance that yourself, to believe me, go right ahead. Okay, so we've got the balanced equation for combustion of propane. Now we need to go ahead and do the math on this. So we write out the given, and we're going to get rid of grams by putting it in the denominator here. And we're gonna put 1 mole of C3H8 up here. So you guys can see this is following the same pattern. We've got the given, and then we go to a molar mass so we can get rid of the grams and get into moles, because once we're in moles, then we can do a mole-to-mole ratio and get to a different substance, and then we can do the molar mass of that different substance to get an answer in grams. But first we have to figure out what the molar mass of propane is, and when we add that up, what we get is 44.11-ish. If you added it all up and you had 44.10, you're good too. Remember, there's some wiggle room in that last significant digit there. The grams of propane cancel out. Now we're in moles of propane, and we need to get rid of moles of propane, so we stick it in the bottom over here. Because remember, moles of propane divided by moles of propane is what? 1. Anything divided by itself is 1. Now, where do we want to get to? We want to get to CO2. So we'll have moles of CO2 here, and this is our mole-to-mole ratio. Now, where do we find the numbers that go in the mole-to-mole ratio? We find them right off the balanced equation. So for every 1 propane we're burning, we're making 3 CO2s. Or the other way you can say it is for every 3 CO2s we make, we had to burn 1 propane molecule, okay? So 3 moles of CO2 are made for every 1 mole of propane that's burnt. Now that cancels out our propane, and we're in moles of CO2. But remember that we don't measure things out in moles. We have to have grams or liters or milliliters or milligrams. And if we use the molar mass of CO2, we can get to grams. So we go ahead, letting our units guide us again and putting moles of CO2 in the bottom there, so it'll cancel out with this guy on the top up here. And we can relate moles of CO2 to grams of CO2 because we know how to do that by this point. And what we find is we have 44.01 grams of CO2, and the moles cancel out. And if you've forgotten how to do a molar mass, what you do is you look at your periodic table and you go, okay, average mass of a carbon is 12.01, average mass of an oxygen 16.00 plus another oxygen 16.00, or you could do the 15.999 version. Either way, you're fine. And then you do 4.3 times 3 times 44.01 divided by 44.11 or 44.10, depending on what kind of sig figs you used from your periodic table. And what we'll find is that we get an answer that is about 12.87 grams of CO2. And are we going to want to leave it like that? No, because the original measurement had 2 sig figs. So this is one of those weird ones that students won't want to answer, and because we all like to have something after the decimal, but these first 2 sig figs are the only sig figs, and we look at the 8 to tell us whether we round the 2 up or not, and we do. So what our answer is with correct significant digits is 13 grams of CO2. And we are done with number 3. Okay, so we've got more to do. Moving on to number 4. Using the equation below, this one right here, we want to calculate the amount of glucose that we started with if we produced 12.76 grams of CO2. So we know how much product that we made, how much CO2 we made, and so we want to go backwards and figure out how much C6H12O6 we started with. This right here is glucose. That is a sugar, and it's very important to us because that's what our cells like to eat. Nom, 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 glucose. Okay, so we've got the balanced equation here. So we don't have the balanced equation here. We have the equation here, and we need to balance it. So this looks a whole lot like a combustion reaction. There's just a slight little change here, but we're going to go through the same process. So with combustion reactions, we balance the carbons, then the hydrogens, then the oxygens. So we have 6 carbons from the glucose. That means that we're going to need 6 carbon dioxide so that we have 6 carbons on each side. We have 12 hydrogens from the glucose, so that means we're going to need 6 waters in order to have 12 hydrogens on each side. And then we can see that on our product side, from the carbon dioxide, we've got 12 oxygens, and from the water, we've got 6 oxygens. And that's a total of 18 oxygens. So what we usually do when we do combustion reactions is we say, okay, there's 18 oxygens on the product side, and over on the reactant side, these oxygens come in 2s. So we're just gonna put a 9 there, and then we'll have 2 times 9, which is 18, and we're done. But what we need to not ignore is the fact that there are 6 oxygens coming from this one glucose over here. So to write 9 oxygens, 9 O2s wouldn't be correct because we already used up 6 of our oxygens from the glucose, so we don't need that part. So what we need is 6 O2s here, so that we have 12 oxygens from our 6 O2s, and we have 6 oxygens from our glucose, and that gives us 18 oxygens on both sides. Okay, so let's do some math. So we're going to start our math with our given. So we have 12.76 grams of CO2. And we're gonna want to get out of grams. So we have grams of CO2 down here. And we have moles of CO2 up here. And this is a molar mass. So we'll do 44.01 grams of CO2 down there. And if we want to go with convention, which states that in our conversion factors we want 1 more sig fig than the original measurement, then we can go ahead and go, oh, okay, well, when I went to calculate it, it was actually 44.009 grams of CO2. Then you're good. and you cancel out the grams, and you're in moles of CO2. Let your units guide you. You want to get rid of moles of CO2, and then you're like, what do I do? Ding, 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 mole to mole ratio. So where do we want to go? We want to go to moles of glucose because it says amount of glucose here. So we say C6H12O6 here. And where do we find these numbers that go in the mole to mole ratio? We find them right off of the balanced equation. So for every 1 glucose that you burn, you're gonna produce 6 CO2s. The other way you can say it is for every 6 CO2s that you make, you had to consume 1 glucose. So we consume 1 mole of glucose for every 6 CO2s that we produce. Alrighty, so moles of CO2 cancel out and we're in moles of glucose. But you know, we can't stop there. We have to go all the way to grams. And this is our molar mass. So we go ahead and we put the 1 next to the moles of glucose because that's what we do. And then we have to figure out how many grams of glucose we have for every 1 mole of glucose. So what we would do is pull out a periodic table and go, okay, carbon's weight 12.01, multiply that by 6, add to that 12 hydrogens, add to that 6 oxygens, and you would find that you had a molar mass of about 180.16. Cancel out the moles of glucose there. Again, if you don't trust me on the molar mass for glucose, go ahead and add it up yourself. That'd be a really good exercise. And if you go ahead and do all the calculations with your calculator, what you'll find is we have an answer of 8.706 grams of glucose. Now again, you guys, if you had a 5 or a 7 there because you had different sig figs over here, that's okay because that very last digit is our estimate and that one has the wiggle room on it, okay? So 4 sig figs, and that is our answer there. Okay, number 5 says how much glucose was consumed in order to produce 100 milliliters of water? And maybe at this point you're like, what? Like, we don't start with milliliters, we always start with grams. Maybe she means milligrams and I can do milligrams. No, and you can do this because we've done density a number of times. So remember, density is going to relate mass to volume or volume to mass. So we've got the balanced equation and we have some kind of numerical given here. So we're just going to go ahead and start with that. So we have 100 milliliters of water. And we're thinking, oh my goodness, I need to get rid of milliliters and I need to get to something that I know. Well, you should know by this point that density is going to relate milliliters and grams because we've done that a number of times and that was chapter 1 plus we had a lab on this. And the one density that I always ask you guys to know is that the density of water is what? A really easy number. It's 1. So we go ahead and we let our units guide us. And for every 1 milliliter of water, we're going to have 1 gram of water. Now, the density of water changes slightly with temperature. And I picked the easiest numerical value. And this happens at 4 degrees Celsius, where it's 1. Now, if we heat up the water a little bit, it would be a little tiny tiny bit less than 1, but we want to go with the easiest value here. So we'll just assume it's 4 degrees Celsius. And for every 1 gram of water, you've got 1 milliliter of water. And for every 1 milliliter of water, you've got what? 1 gram of water. Okay, so we can see that the density of water is 1. But the best thing about that is we got out of milliliters, which probably was freaking you out, right? Yeah. Okay, and we're in grams. So now we know what to do because we've been doing all these problems starting in grams. So we're in grams of water here, and we want to go where? We want to somehow get to grams of glucose. So that means that we have to go through moles. We have to get to moles because we want to eventually get to a mole-to-mole ratio where we can switch from water to glucose. So, okay, let's go ahead and put grams of water here and put 1 mole of water here because we want to get to moles of water. And we already added this all up, and we got 18.02, but right here we can see that we've got 4 sig figs. So we tend to want to put 1 more sig fig in our conversion factor. So the 18.02 was actually 18.015. So we'll go ahead and cancel out grams of H2O. And then what we will do is we will go ahead and do a mole-to-mole ratio. So what we have on the bottom here is moles of water, and on the top we have moles of glucose. And where do I find those numbers right there? You find them off of the balanced equation. So again, if you don't balance your equation correctly, you're gonna get your math wrong. Okay, so for every 6 waters that I produced, I had to consume how many glucoses? 1 right there. The other way we can say that is for every 1 glucose we consume, we're going to produce 6 waters. Or for every 1 mole of glucose that we consume, we produce 6 moles of water. So the moles of water cancel out here, and then we're going to need to do one more step because we don't measure things in moles, we measure them in grams. So if we have 1 mole of glucose, we're going to have 180.16 grams of glucose. And where on earth did I get that? We did that right there. Okay, and then we're gonna do the math on this. So moles of glucose cancel out there, and I'm gonna do a little bit of erasing. So I have some room down here to write this. Okay, stick those 6's back in there. And then on your calculator, you go ahead and do 100 times 180.16 because you have 1 and 1 and 1, and you can do times 1 times 1 times 1 if you want, but don't need to. And then we're going to divide it by 18.015, and you'd probably hit the equals at that point, and then divide it by 6. And what you would get on your